Hello everyone. So in this episode I'm going to talk about how we can observe a target of either large-scale structure, astronomical object, or quantum mechanical small-scale structure objects when we have some contamination in our sample using extra dimensions. Here you can see a distribution of either galaxies or small-scale particles, and we have different kind of colors. So the green ones are the targets, the ones that we will actually want to observe because they are particular interest for our study, while we have other colors such as the red and the orange and the blue ones that are contaminating our sample. So when we talk about astronomical and quantum objects together, we talk about cosmological objects, so the largest and the smallest scale structure of the universe. So this study that can be expressed using this kind of heavy formalism can be applied to all kind of scales. And I'm going to explain this kind of formalism slowly in the next part. So basically, I'm going to describe this in some spatial space and some temporal time, and then I can add extra dimension to that. And I'm going to talk about specifically about targets and contaminated targets, which are applicable to cosmic structure, mainly large-scale structure, astronomical ones, and small-scale structure, quantum ones. So how do we make observations in astronomy and cosmology? Basically, we ask the question how to distinguish an identification line properly. So we talk about the line identification effect. How does this work? Now let's imagine that we have this observable universe and we have our targets here. However, we don't have only targets in our experiments. We usually have contaminants, either coming from early times, high redshift, Z, or late times, low redshift, Z. Now, these are our actual targets, but here we have wrong targets and we would like to model it. Now, let's talk about line identification. We have a galaxy out there and we have some detectors hereby. We have ground-based telescopes such as DESI and LSST, or satellite telescopes that go around Earth and the Sun, such as Euclid. And the galaxy is going to emit some light, and the detectors are going to detect it as a line, which is the signal light coming from the galaxy, and tell us a lot of information about the universe. Now, how this works in our instruments. Let's say that this galaxy is emitting this kind of line, and we have two particular lines. We have the oxygen 3b and the hydrogen alpha lines. Now, when we make a measurement of this flux, we have a graph that looks like this. So if we define a threshold like this one, we can clearly identify the different heights of these lines, and we can identify clearly the hydrogen alpha and the oxygen 3b line. However, when we make observations, we have some problems, and we have some noisy instrumentation, low signal-to-noise ratio, or noisy flux measurement, or low detectability due to the fact that we have contaminants in our sample. And when we have a measurement, this would look like this. So these three simple thresholds no longer tell us which line has a higher height. Therefore, we're confused and we don't know which one is which. In reality, we have a graph that looks like this. Therefore, we have particular problems that we need to solve. However, there is a treatment to this problem, and it works like this. So a line misidentification treatment works as follows. We assume that a galaxy has a wrongly identified wavelength, lambda w, which is related to a correctly identified wavelength, lambda c, via this formula, where we know the redshift of the wrong galaxy and the redshift of the corrected galaxy. So then we have to model the number of wrong galaxies, the fraction number of wrong galaxies over the total number of galaxies in our sample. And then an observed galaxy is going to be observed at a new position y, which is a distorted one according to some factors gamma of the previous position x. So a galaxy at the position x is going to be observed at the position y, which is right into our the region where we would like to observe our actual targets. Therefore, the overdensity is affected as follows. We have the observed targets, and this includes the wrong targets, the contamination, and the actual targets that we would like to observe. Now, by knowing and modeling this type of equation, we can make estimates about the universe, and we would like to see how the actual targets are evolving as a function of space-time, but we can decouple the wrong targets in our sample that are probably stars, and they don't have the same evolution as the galaxies. Therefore, by doing this kind of estimate, we can clearly identify the two different sources and have a corrected kind of observation. Now, this was modeled firstly by Pullen et al. In 2015. Now, we're going to build on this model by considering extra dimension and a lot of amount of observed targets and contaminants. And this works as follows. Now, this kind of instrumentation and methodology is going to be used by Euclid. And here on the top left side, you can see the specs of the Euclid telescope that is going to be located at the Lagrange point 2 around the Sun. And here, Euclid is going to observe galaxies in a wide field to make estimates about the evolution of the universe. However, there are going to be a lot of contaminants, galaxies coming from high redshift or smaller redshifts. So in order to identify clearly what is happening before and after to this wide field, Euclid is going to drill into two deep fields. And in these deep fields, he's going to estimate the amount of correct and the wrong kind of galaxies in the deep field. So by making accurate estimates of the amount of tracers in these deep fields, we can correct now the wide field. And then we can do some data analysis in order to disentangle between different models and see which model describes better the wide field and the evolution of the universe. The same kind of technology is going to be done by Roman telescope in some later years. Now, we're going to model this effect using extra dimensions. And, extra dimensions are described by this kind of equations that are a bit complex, and I will need another 15 minutes to discuss that, so maybe in another video. But here I'm going to simply describe these ideas by taking the observed density into 4-dimension and then adding extra dimensions, simply as follows. So we built the radial spatial dimension, which is also curved due to the amount of mass and energy around it. And we have the temporal dimension here. Now we can add some angles and we can build extra dimension on the spatial space, and we can add also some extra time dimension in this one. Therefore, by simply adding dimensions in our formulation, we can consider this extra dimension on our observations as well. How this is done? Basically, all targets are in the extra time and space dimensional target manifold. And we have the extra dimensional contaminant manifold from early times and from late times, as done before. Now, by considering these ideas, we can basically rewrite the equations that Pullen et al. Wrote, and we can simply write it as follows. So for n targets of the observed large-scale structure of the universe, we can have the observed density, delta omega, in extra dimension, extra time, tau nr, extra spatial. And this is equal to the theoretical matter power spectrum to some initial time and some boundary spatial space, and times FBD functional factor in extra dimensions as well. Now, this FBD is the whole point of this paper. So basically, we can describe all the contaminants and their biases and the growth of structure of our tracers and the contaminants by using this kind of functional. And in this functional, we have all the sum of all the targets from the first target up to the n target of observed large-scale structure, consider all the contaminants for each of these targets, N, C, T, and then have the factor of contaminants, the bias of the targets and the contaminants, and the growth of structure. And the first term describes the amount of actual targets, and the second term describes the behavior of the contaminants. Now, under some reasonable assumptions, we can assume that there is a scale-independent contaminant factor. Therefore, all these extra dimensions only depends on temporal time dimensions. And when we do that, then the observed power spectrum, which is the observed Fourier transform of the energy density over the theoretical power spectrum of the matter over density, is equal to this contaminant functional, FBD, as a function of time and to some power n. And n gives us the amount of correlation, the amount of statistics that we're looking in our sample. For n equal to 2, we look at 2 galaxy statistics. For n equal to 5, we look at 5 galaxy statistics. Now, by modeling this effect, we have a description about the extra dimensions, and we also combined the observed and the contaminant observations in our sample. Now, we can describe in 1 time and 3 spatial space, and we can build some graphs in that. We can do that for higher dimensions as well, but here I'm giving a simple example for the 4 dimensions that current telescopes are looking for, but in an extra study we can build graphs that look more dimensions. Now, in this particular example of 4 dimensions, we can see the following. This FBD functional to some power n as a function of redshift or time. So the lower the redshift, the later the time. The higher the redshift, the earlier the time. So we see that at late times, low redshift, we have a high value for FBD, the functors, bias, and growth of structure, while for early times, high redshift, we have low bias and growth of structure. And this gives us the information about the bias and the growth of structure, and given in blue. This is when we look at 5 galaxies at the same time as a correlation. Now, the red curve tells us about the contaminants in our sample. And basically here we consider a sinusoidal function, and therefore that's why we have a sinusoidal part in our graph. And you see here, the more contamination we have, this value of FBD is higher. Therefore, by knowing the expression and the graphical description of this FBD without contaminants and with contaminants, we can build scenarios about how much contamination we have in our sample, and then using data, we can identify clearly what is the amount of contaminants in our sample by fitting this kind of parameters in our data. Now here, the blue line is for n equal to 5, so we consider statistics with only 5 galaxies at the same time. And this particular contamination is behavior is coming when the contamination is coming from higher redshifts. If the contamination is coming from low redshift, we have a slightly different behavior, but overall the effect is the same and it is controllable, and we can use this kind of modeling in order to have control observations and corrected and efficient observations as well. Now, here you can see for different levels the different amount of correlations. The lower the value is when we consider 2 correlators, 2 galaxies at the same time statistics. The middle is when we consider 3 galaxies at the same statistics, and the high one is when we consider 5 galaxies at the same time statistics. Therefore, by using this kind of estimates, we can have a control fitting to our data. Now, we discussed that in large-scale structure, we can also describe the same thing in small-scale structure. And here you can see a quantum field phi, which can be decomposed to a universal phi field to some boundary and initial conditions, time initial and x be some boundary. And then we can discuss about the targets of these quantum fields and consider also the amount of growth of this field as a function of time and space, the actual amount that there is from the targets, and of course the term that discuss the contaminants. Now, all this can be describing the quantum contaminant factor, CTF, and we can build quantum correlation that basically integrate the universal field phi, but also the quantum contaminant factor up to some exponent which gives us the probability of this field, which is related to the action itself. And now by using this kind of formalism, we can use now observational data from Large Hadron Collider or other kind of colliders and have a controlled observed quantum field density field. So as a take-home message, I would like to discuss that these ideas incorporate extra dimensions. So we can build in our mathematical models into extra dimension and try to see how observable measurements can impact these estimates from extra dimensions. And this is applicable for targets and contaminated targets in order to have some control estimates of how the quantum fields, all the astronomical fields are evolving as a function of time and space. And therefore, this is applicable to cosmic structures, to large-scale structures, astronomical ones, and small-scale structures, quantum ones. I would like to thank you for your attention, and if you like it, subscribe for more. See you to the next episode.